Good day, ladies and gentlemen. You're all welcome to CMEN405 lecture. This is our lecture number 3, and I decided to divide it into 2 parts for simplicity. In this lecture, the first thing we're going to look at is sequential logic. If you can remember, in our lecture number 1, we said we have 2 types of logic: combinational and sequential logic. We have already discussed about combinational logic, where we said it is logic whose output depends on the present input only. So here we are on sequential logic. As you can see on this block diagram, the sequential logic is made of 2 things. We have our combinational logic, taking the external inputs, and we have our memory element, which keeps the previous output of the circuit, and we have a feedback network that takes this memory content to the combinational logic. So we can now say our output for sequential logic at any point in time depends on 2 things. One is the external input, and number 2 is the feedback, which is the previous output. Now we can say that the sequential logic has memory elements and it has a feedback network. Types of sequential circuits. This sequential circuit also is divided into 2 types: synchronous and asynchronous. The synchronous sequential logic, they are the ones that are operated using a single or a common clock. All the components in that circuit or in the system, they are operated using a common clock. While the asynchronous, they are the ones that don't have a common clock for their operation. Yes, they may have clocks at different points, but they don't have single one driving all the components in the circuit. And we have seen that in sequential logic, we have a memory element. This memory element is what we call a flip-flop, and the flip-flop has a storage capability of only 1 bit. That is, it can store either 0 or 1, only 1 bit. And of course, these flip-flops, they are of different types, as we are going to see now. First of all, we look at the basic flip-flops, and these basic flip-flops, they are fabricated using what we call universal gates, that is NOR gates and NAND gates. So this is the block diagram or the circuits, logic circuit of the basic flip-flop using NOR gate. We have 2 of them, gate 1 and gate 2. And as you can see, each of these 2 gates has an external input. This one has reset, this one has set, and the output of this one is taken as feedback into the second gate. Likewise, the output of second gate is taken as input into the first gate as feedback. Now, if we want to analyze this one, we need to remember the operation of NOR gate. We can remember that the NOR gate gives 1 only when both the inputs are zeros. But whenever you have at least 1 0 or all of them are 0, your output, 1 or all of them are 1, the output should be 0. Now, based on this, let us look at the truth table for the operation of this basic flip-flop using NOR gates. The first line here gives us our set signal is 1 and the reset is 0. Now, if set is 1 and the reset is 0, you know that since we have one of the input to get 2 as 1, automatically the output should be 0. And this output is now going here together with my reset, which is 0. So I have zeros entering this gate 1, and definitely my Q should be 1. The second condition is we change our set to 0, but the reset is not changed to 1. The reset is not changed to 1. Now, it means our reset is 0 and the set is also 0. But we should remember that our previous output Q was 1. So since one of the input of this gate 2 is 1, definitely this my output should be 0. This 0 together with my 0 reset should give me 1 again, and look at it here. The next one is where we said we change our reset to 1 while the set is 0. In this case, you can see that one of the input to get 1 is 1, which makes the output automatically to be 0. So this 0 together with my set, which is 0, should give me 0 0 1, as you can see here. And the next condition is when we change our reset to 0 but keeping our set at 0 again. so we have zeros here, but we have to look at our previous output, which is 0, which means both the input of gate 2 are zeros, the output should be 1, and this one together with anything from my reset should give me 0 again, and that's what we have. So the last condition shows the limitation of this basic flip-flop, because wherever you have your set equal to 1, reset equal to 1, automatically the outputs of gate 1 and 2 should be 0 0 based on the truth table of no gates, and this is never acceptable because the Q and its complement cannot have the same value. So this is the setback of this basic flip-flop. The next one is our basic flip-flop using NAND gates, and for us to analyze it we have to remember its truth table. For the NAND gate to give you 0, all the inputs should be 1, but whatever other conditions we have, whether we have 0 1 or 0 0, the output should be 1. So based on this, we go to our truth table where we have our set equal to 1 and the reset is equal to 0. So since one of the input to this gate 2 is 0, automatically my output here should be 1. It is taken here as feedback, and my set is 1. 1 1 should give me 0 here. This is what I have. My Q is 0 and my Q prime is 1. Then if you now change your reset from 0 to 1 but you didn't change the value of set, it remains 1 1. Now it means the both inputs to this gate 1 and 2 are 1 1. But let us look at our previous output, which is 0. This 0, which is the previous output, it comes here to gate 2, and since one of the inputs of this gate 2 is 0, the output should be 1. So this one is taken as feedback to gate 1, making the both input 1 1, and my Q still remains 0. Therefore this is my Q 0, Q bar is equal to 1. If you look at the next condition where set is 0 and the reset is 1, since one of the inputs to this gate 1 set is 0, automatically I have 1 here. This one coming here together with my reset, which is 1 1 1, should give me 0, and this is what we have. The last thing is when I have both of them equal to 1 1, but I have to look at my previous output Q, which is 1. So it means I have my reset 1, my feedback 1 1 1 should give me 0, and this 0 coming here will give me 1. That's what I have. Its own shortcomings comes when your set and reset are all zeros, because whenever one of the input of this gate 1 and 2 are zeros, automatically the output should be 1s, and this is not acceptable because the Q and its complements can never be the same. So it is based on this shortcomings of these basic flip-flops that modified versions of the flip-flops were developed, and these include RS flip-flop, D flip-flop, JK, and the T flip-flop. Now we start looking at the first one, which is RS flip-flop. If you look at this block diagram, this is our original basic flip-flop using NAND gates. The only modification is introduction of these two gates, gate 3 and 4, and we have a CP, that's our clock pulses driving the gates. Now here I can see I have my two external inputs, set and reset, and I always consider my previous output Q. So I have my truth table having three variables, Q, R, and S, and they will follow the normal binary sequence 000, 001, 010 up to 111. Now let us analyze. This clock pulse is always equal to 1. If you look at the first line here, my set and my reset, all of them are zeros. So since one of the inputs of gate 3 and 4 are zeros, I can automatically say the output here is 1 and the output here is 1. So I look at my previous output, which is Q, 0 taken to this place, which means one of the inputs of gate 2 is now 0, making the output to be 1. This one will go together with my output of gate 4, which is 1 1 to give me 0, and this is what I have. Next condition, I have S0R equal to 1. So if S is equal to 0, automatically my output here should be 1. But here my R is equal to 1, my clock is 1, the output should be 0 here. So this output serving as 0 should make the output of gate 2 equal to 1, because one of the inputs is 0. So this one together with my output from gate 4, which is 1 1 1, should make the output to be 0, and here we are. The next condition is when I have S equal to 1 and R equal to 0. Now if S is equal to 1, my clock is equal to 1, 1 should give me 0 here. And if my R is 0 and my S is, clock is 1, the output here should be 1. So since I have 1 here, but here I have 0, so regardless to what is coming as the feedback, this 0 will make the output of gate 1 to be equal to 1, as you can see here. Now if you go to the next condition where your S and R are all 1 1, we will have something like this. We will have something like this, because here I have 1, here I have 1, and my clock is also 1, making the inputs to gate 3 and gate 4 to be all 1s, and the output will automatically be 0 0. So if I have 0 here, 0 here, the output of my gate 1 should be 0, gate 2 should be 0, meaning my Q, 1 1, meaning my Q is 1 and Q bar is also 1. This is what we call indeterminate states. Therefore still this one failed to solve the problem we have seen in the basic ones. And also look at the last condition where S and R are also 1 1 together with my clock pulse, which is 1. So the output of this one should be 0 and this one should be 0. So if I have 0 0 here, gate 1 will give me 1, gate 2 will give me 1, which is also indeterminate condition. Okay, so now the next thing we'll do is to use this our truth table to derive our next state equation for the modified RS flip-flop. And this is what we do. We have 3 variables here, Q, S and R, and I use my Cannon map here. I fill in the values. These XX, they are for these indeterminate conditions. We take them as don't care conditions. Here we combine these 4, and you can see moving from this row to this row, the value of Q has changed from 0 to 1, and moving from this column to this column, the value of R has changed from 1 to 0. The only thing that remains the same is S, which is 1 1. So see it here. And if you take this square and this one, they are adjacent if you fold the Cannon map. And you can see that along this line my Q does not change, but moving from this column to this column, the value of my S has changed from 0 to 1, but R remain 0 0. That's why I have my R prime and my Q. This is the next state equation. And of course these flip-flops, they are fabricated in form of integrated circuit. So this is the block diagram of the flip-flop. This is my S terminal, R terminal, this is my clock, and this is my Q and the Q bar. The next one is we look at the D flip-flop. This D stands for the delay, and the reason why this one was developed is to eliminate the problem of this SR flip-flop, which we have 2 indeterminate conditions. And if you look at them carefully, these indeterminate conditions exist only when S and R are both 1 1 here and here. So in order to eliminate that, we now introduce another NAND gate, and it is operating as an inverter. Remember our first lecture, which means if my input now D comes, the real value will come here and it will be inverted before it go to gate 3. And this is to tell us that we eliminate the possibility for gate 3 and 4 to have 1 1 as the input at the same time. So now I can see I have only 1 input and I have my previous output. So my truth table will have only 2 variables, D and Q. Let us take an example. Let's say our D is equal to 1. If D is equal to 1, this one will come here, and together with my clock, which is 1 1 will give me 0 as my output. In as much as here is 0, it means one of the input of gate 1 is 0. My output should be 1 automatically. But in a situation where my D is 0, that 0 will come here together with my clock. So I have 1 here. Okay, so if I have 1 here, the next thing that will determine what will happen is to look at my previous output. In the previous case we said Q is 1, which means Q bar is what? 0. So if this Q bar is equal to 0, I will have 1 0, and that will give me 1. Now, for us to understand this clearly, let us look at the truth table. Look at it. I told you we have two variables, Q and D. So they will have 0, 0, 0, 1, 1, 0, and 1, 1. So in order to analyze this, we take the first condition where D is equal to 0 and our Q at that point is equal to 0. If D is 0, here I will have 1 and my Q is 0. Together with that 0, if we said our previous Q is equal to 1 and D is 0. So now when I have 0 here, together with my 1 should give me 1 as my output here. And my that 0, if it enters here, it will give me what? It will give me 1. This one together with my clock pulse, which is 1, should give 0. Since I have 0 here, it means the output of gate 2 should be 1. This one together with my 1 should give me 0. So all we are saying is that if you look at this one, your value of D is always equal to the value of your nested output, Q of T plus 1. And here, if I want to generate my nested equation, I have only two positions where I have 1, here and here. The first one is 0, 1 and the other one is 1, 1. Combining this, you can see the value of Q has changed, but the D remains 1. So Q of T plus 1 is always equal to D. Whatever is the value of D is the value of output. And this is my block diagram for the IC. And this is my D, this is the clock, this is my Q, and this is the Q bar. So the next thing is to look at our JK flip-flop. And this JK flip-flop, we use our J terminal as our reset and K as the reset terminal. And whenever this J and K, they are equal to the logic 1, the flip-flop will switch to its complement. That's when it was 1. If you have J and K 1, 1, the state will change to 0. And if you have it again, it will change to the 0 again. Let us look at the block diagram, the circuit diagram. Look at it. If you look at it, this is our basic flip-flop using NOR gate, but we now incorporated 2 additional AND gates with 3 inputs. And we know for AND gates to give you 1 as output, all the inputs should be 1. And now you can see I have external input K, external input J, and my previous output Q. So I have 3 variables, Q, J, and K. And you draw a truth table in the normal way, 0, 0, 0, 0, 0, 1, up to 1, 1, 1. Let us analyze. Take the first condition here where J is 0 and K is 0. If J is 0, K is 0, regardless to what is the feedback, what is the clock, the output here should be 0 and the output here should also be 0. So for NOR gate, if you can remember, it will give us 1 only when both the input are 0, 0. So I have 0 here and I have 0 here. But let me look at my previous output, which is 0. If it comes here, it means both the input of gate 2 are 0, making my Q bar to be equal to 1. This one taken to get 1 will automatically make the output 0 as we have here. Let's take the second condition. J is 0, K is 1. So if J is 0, automatically I have 0 here. But my K is 1. So clock is also 1. But what is my previous output? 0. So it means this one of the inputs of this gate 3 is 0, making both of them 0, 0. So if both of them are 0, 0, the next thing I will do is to look at my previous output there, which is 0. This 0 together with this 0 will also give me 1. And this one coming here will make the output to be 0. Look at it. If you go to the next, that's stage 3, my J is 1 and K is equal to 0. So if J is equal to 1 and my clock is always equal to 1, and my previous output Q is 0, which means the Q bar should be 1. So all the 3 inputs of these gates are 1, so making the output here to be 1. But here my K in that condition line 3 is 0, making this one to be 0. So if I have 1 here, automatically the output of gate 2 should be 0. So this 0 together with my 0 will give me 1, and look at it. Let's jump to the last stage where my J is equal to 1 and K is also equal to 1. And my previous output at that point is also equal to 1, which means this one is 1 k is equal to 1, clock is 1, everything is 1. Here I have 1. And since one of the inputs of gate 1 is 1, automatically I have 0 because it is no gate, and look at it. So you follow it continuously, you understand the logic. Now the next thing we do is to derive our next state equation, and that should be done using simplification by Math. And if you look at this, my next state, I have 1 1 1 1, 4 of them, and look at how I fill them. Combining these two will eliminate k, and my q prime is there, so I have j q prime. And if you combine these two, q is there, but moving from here to here, the value of j has changed from 0 to 1, but k remains 0 0, so I have k prime q, and this is the symbol as in the previous case. The next thing is what we call T flip-flop, and this T stands for toggle. Toggling simply means if your state is 1, when you supply logic 1, it will toggle it, it will switch it to 0. If you supply another logic 1, it will toggle it to 1, it will keep on alternating. And if you look at this diagram, it is just our circuit for JK flip-flop. The only thing is that instead of using J and K separately, we tie them together and we call that our T input. That's the toggling input. Now in this case, you can see my external input is only 1 T, and I have my previous output Q. So this is the truth table 0 0 0 1 1 0 and 1 1. Now how do we get this next state's output? Let's take the first condition, that is my T is 0. If T is 0, it means one of the inputs of gate 3 and 4 are 0 0, making the output to be 0 0. Okay, but what is my previous output is 0, so I can say both the input of gates 2 are 0 0, the output should be 1, and this one coming here will make this one to be 0. Take the second condition, T is 1, clock is always 1 as I said, but my previous output Q is 0. So if one of the input of gate 3 is 0, here I have 0. But when Q is 0, it means Q prime is 1. So all the inputs to this gate 4 are what? 1 1 1. So the output here should be 1. Because of the fact that one of the inputs of this gate 2 is 1, automatically I will have 0 here. This 0 together with the 0 coming from gate 3 will give me 0 0, and this should be 1. Look at it. And if you go to the next case, my T is 0, which means I have 0 0 here, but my previous output there is 1. That one coming here will make one of the inputs of gate 2 to be 1, therefore the output should be 0. This 0 together with my 0 from gate 3 should give me 1 again. The last condition is when T is 1 and the previous Q is 1. So if T is 1, the previous Q is 1, the clock is 1, it means everything here is 1, I have 1. Automatically the output here should be 0. So what we need to notice here is that, see, when our T is 0, the output is what? 0. But the moment it changed from 0 to 1, the output toggles, it changed to 1. When T changes to 0, nothing will happen to the output until when it changes to 0, then it will toggle it. And from this truth table, we have 2 points where I have 1, and I draw them in a truth table, Kano map here. You can see these 2 squares are not adjacent, therefore you cannot further simplify them. So taking here, I have Q prime T, taking this one, I have QT prime, and look at them. This is the circuit symbol. I have my T input, this is my clock, and this is my Q, and this is my Q bar. Now to further illustrate that toggling effect, let us take this equation and say, okay, when our T is equal to 0, put it here. If T is equal to 0, when you come here, your T should be 0. 0 multiplied by this Q prime, it will go to 0. But when T is 0, T prime should be 1. 1 times Q should remain as Q. It will remain as Q. But when T is equal to 1, let's come here and substitute. When T is equal to 1, the T prime should be 0. 0 times Q should be 0, which means 1 times Q prime should be what? Q prime. So what we are saying is that whenever T is 0, the output remain as the previous Q. But when T changes to 1, the output will now toggle, it will go to Q prime, and that is why we call it T flip-flop, and that's the toggling effect. So the next thing is analysis of sequential circuit. If we are given a sequential logic circuit and we are asked to analyze it, the first thing we do is to investigate and see whether it is sequential or not. And how do we identify that? We check for flip-flops. Wherever you see a logic circuit containing flip-flops, then you can conclude it is sequential in nature. After that, the analysis, you can be asked to obtain the next state equations for the circuit. You can also be asked to obtain the state table from those equations, and finally draw the state diagram of that circuit. And you can be asked to go in a reverse process. That is, you can be given state diagram, from it you derive your state table, from it you derive your state equations, and finally draw the logic diagram. That is the reverse process. And for us to understand this, let us take a typical example. We are given this like logic diagram, and we are asked to obtain its next state equations, to draw the state table and the state diagram. So the first thing, as I said, we have to scout and see, do we have any flip-flop? Yes, we have two of them, D flip-flop here and another D flip-flop. So for us to analyze this, all we need to do is we go here. This is our logic diagram. This is AND gate, another AND gate. The output of the two enters OR gate. This is AND gate, three of them, and they enter OR gate. And we should remember that for D flip-flop, the next state equation Q of T plus 1 is always equal to D. That is, whatever is our D is our next output. Now, the first thing I will do is to determine what are the input to this first level of gates, and from there we get their output to serve as input to this OR gate, and finally determine what are our Ds. How do I do that? I will say, okay, this point, if you look at it, let me follow it. It is from A, so I'll put A here. And the same line extends to this gate, so I'll put A here also. But if you look at the other inputs, tracing it will lead us to this point, which is B prime. So I have B prime entering here and the same B prime entering here. Then if you come to this gate, one of the input is from here. You see, this is external input X, and we pass it through an inverter. This should be X prime. But the other one, look at it, it is coming from B here. So doing this, I trace all the origin of the input. That is my first stage gates, and then I look at this one and say, what type of gate is this? This is AND gate. So I have A and B prime going in, and my output should be AB prime. The same thing with this, BX prime. Same thing with this, A prime X, up to the last one that has three inputs, A, B, and X prime. Now, if I want to get the output of this, all I need to do is to say, okay, this is an OR gate, and for OR gate, I will add the input coming, that is AB prime plus BX prime. And for this one, I have three, that is A prime X plus B prime X, and finally A, B, X prime. So these are the these are the two inputs to my flip-flops, D and D. But you should look at this, that this D flip-flop, we call it A, and the other one we call it B. So instead of using Q of T plus 1, we should use A of T plus 1. So if you go back to this my simplified diagram, you can see that what is coming to this D is equal to AB prime plus BX prime, and that is exactly what I have here, AB prime plus BX prime. You see, I put T here to show that it is a function of T. This is the previous, and then A of T plus 1 is the next output. And the same thing applies to this. If you combine this and this passing through OR gate, you add all of them to give us A prime B plus A prime X plus B prime X plus AB X prime. And this is exactly what I have here. So I obtain my two state equations. But going back to our diagram here, you can see that I have an external output, and this external output is taking its source from here. So whatever is coming to this place should be my value of Y. And if you go back to this diagram here, you can see that what we have here is b prime x, so therefore my y should be b prime x, all of them of t. So after doing this, the next thing is to draw my state table. The first two columns should represent my present states, and you know we have only two flip-flops, A and B, so I have A and B. But at the same time, we have an external input x from diagram here. So the three variables on this my present state should be A, B, and x as my inputs. Then the next state should be for A and B, and then my output x. So in order to determine the x state, the values for A, the values for B, and the values for y, all I need to do is to use these equations. Let me illustrate how to do that of A. If you look at that of A, the first row here give me A is 0, B is 0, and x is also 0. You see, if A is 0, this is A multiplying by anything, it should be 0. And if B is 0 multiplied by anything, it should be 0. So I can conclude that my A at this point should be 0. If you go to the next one, 0, 0, the same thing applies. Let's go to the third line here. My A is 0 and my B is 1. So if I come here, because of the fact that A is 0, this A times this B should go to 0. But B is 1. But what is my x at that point? The x is 0. The complement of 0 should be 1. So I have B1, complement of x is also 1, 1, 1 should give me 1. And 1 plus anything in Boolean algebra is equal to 1. Look at it. So you do the same thing to the rest, do the same thing for B, you do the same thing for y, and this should give you your state table. So the last thing we should do is to use this state table to draw our state diagram. And how do we do it? If we want to do that, we look at our variables. We have only two flip-flops, A and B. So you can see here my A and B are 0, 0, here are 0, 0. And here we have 0, 1, 0, 1. Here I have 1, 0, 1, 0. Here I have 1, 1, 1, which means I have only 4 combinations. Either 0, 0, or 0, 1, or 1, 0, or 1, 1. 4 of them. So I'll now come and say, okay, these are my 4 combinations. 0, 0, 0, 1, 1, 0, and finally 1, 1. The next thing I will do is to come and say, okay, when in this first row AB is 0, 0, what is the next output? Is also 0, 0. It means it is moving from itself, going back to itself. But we have to look at the conditions under which this happened. My x at that point is 0 and my y output is equal to 0. So I'll now say, okay, from 0, 0, I will draw a line coming back to 0, 0, but this one stands for x slash this one stands for y. Then going back, look at the second one. When I have 0, 0 here in the present state, my next state output should be what? 0, 1. Meaning we should move from 0, 0 to 0, 1. But what is the condition? We look at this and say our x at that point is 0 and the corresponding y is also 0, and that is why I am having 1 slash 0. Let me take maybe the last one for 1, 1. When AB in the present state are 1, 1, my output is going to 1, 0. Look at it. This is 1, 1. I'll go back to 1, 0. Then going back to the table and say, okay, my x at that point is 0 and my corresponding y is also 0. That is why you see here 0 slash 0. And the last one here from 1, 1 to 0, 1. Look at it. From 1, 1 we go back to 0, 1. But what are the values of x and y? My x is 1 and the corresponding y is 0, and look at how I put it, 1 slash 0. So ladies and gentlemen, this is the end of our lecture number 3 of CMEN405 part 1. We are going to continue and discuss on the second part of the lecture 3. Thank you very much, and till we meet in the part 2.